half cells today. Reference half cells. So what is a reference half cell? The most common, get your data booklets out today, guys. Data booklets out. Most common, or the most common half cell we use is the hydrogen half cell. And in your data booklet, you'll see that find hydrogen half cell. I'll give you a little hint. If you look along the right-hand side, since we're talking about electrical potentials and things like that, for that half cell, it's got a 0.00 volt electrical potential. So we use that as the reference half cell. Every other half cell, basically every other reduction half reaction on that page, is directly related to that hydrogen half cell. Okay. For example, fluorine half cell, the very one at the top, makes 2.87 volts, okay, is the electrical potential compared to that hydrogen half cell, okay? And just like the very bottom one, negative 3.04 for the lithium ion reduction half cell there, that is in comparison to the hydrogen half cell. In other words, it's 3.04 volts below that hydrogen half cell. So we're going to talk about half cells today, okay? The most common one, like I said, is the hydrogen. That's what all that table is based on. It's based on the hydrogen half cell, okay? A reference half cell is used to determine the relative reduction potential of other half cells. A reference half cell, and this is important and you need to know this, always has a potential of 0.00 volts. In your data booklet, the hydrogen is the half cell. Okay, is the reference half cell. A standard hydrogen half cell is commonly used as a reference half cell, and of course it has a potential of 0.00 volts. So like I said, everything is based on that according to your data booklet. Okay, so if a half cell contains an oxidizing agent, okay, oxidizing agent stronger than H+, it will have a zero electrical potential, basically, or of greater than 0.00 volts. So think about that. If the oxidizing agent is stronger than the hydrogen half cell, right? What does that mean? The oxidizing agent is stronger than the hydrogen half cell. It's got to be higher, right? In other words, if you take a look at that data booklet, guys, again, and you see 0.00 hydrogen half cell, and you think, okay, the oxidizing agent's stronger than this, well, it's got to be higher than that, right? And we know that if it's the oxidizing agent, it's being reduced, correct? So that would be the cathode, right? Which would leave this, of course, as the anode, and the cathode minus the anode would be a positive, right? Because those numbers are all greater than the 0, right? So whatever one you want to pick there. And vice versa, right? So if the half cell contains an oxidizing agent that's weaker than that hydrogen half cell, and when we talk about the hydrogen half cell, just like we've been doing, you can talk about the H+, you can talk about the H2, it doesn't really matter. That's the half cell that takes place in either the cathode or the anode. Okay, it's one of the two, it doesn't matter. But that half cell, okay, if anything's below, or I guess, what is it? If the oxidizing agent's weaker than that half cell, okay, it's going to have electrical potential less than 0. Okay, so in that case there, you know, once again, your E net would be a negative in that case. All right. If a different reference half cell had been selected, the individual electrical potential would be all different, but the relative difference between them would remain constant. And that's a little bit wordy for me to say that. What we're saying is this, okay? Listen. On this data booklet, everything refers to the hydrogen half cell, that's 0.00 volts. What if I decided that I didn't want to use the hydrogen half cell as the reference half cell? What if I decided I wanted to use, I don't know, what's right above hydrogen there? Let's say tin 4 plus is a couple above there. What if I wanted to change that to the reference half cell? What if I wanted to make that one 0 volts and compare everything to that half cell instead? Okay, Well, that's what we're going to talk about here now for a little bit. What's going to happen is the numbers are going to change, right? Sure they are. However, what we're saying is this, and this is the important part of it. If you don't understand any of that, that's okay for right now. The importance is this. Okay, let's pick two of them, for example. Let's pick the hydrogen half cell, which is 0.00, and let's pick the copper 2+, which is about 5 or 6 above it. Check it out. Look at it. Okay? Got it? Where'd my booklet go here? I'll just grab this one here. What's the copper one? What's the copper half cell electrical potential? 0.34. So here's the important part. If I'm comparing 0.34 to 0, that's a difference of 0.34, correct? Okay? That's always a difference of 0.34. That difference is always the same. Okay? So if I pick a different cell, for example, okay, which doesn't really make sense with the hydrogen and the copper one, the difference has to remain constant. So you can see, for example, that the copper half cell is 0.34. What's the one? What's the one below it? What's below copper there? Okay, so SO4, sulfate and acid one, right? And that's 0.17, yes? Okay. The difference between copper to that acidic sulfate one there is always the same. It's always 0.17 difference. No matter which cell I want to use as a reference half cell, okay, it doesn't matter. That's always going to be the same difference. Okay? So whichever one you pick on here, if I pick one up here and here, they're the same difference apart all the time. Okay? The numbers may not be exactly the same, but it's going to be the same difference between them all the time. This never changes. Okay? What I'm doing is I'm changing which one I'm going to use to reference the other ones, basically. Okay? And we got a table for you to do that with here on the next page here. So we're going to do that and take a look at that. So, okay? Unfortunately, mine's really big here. But look, across the top you have the reference half cells. So don't worry about, there's copper and zinc over here. Don't worry about those. Let's just focus on this hydrogen one right now. Okay? If I use, basically here's how it works. If the reference half cell is hydrogen, that has to be what as far as electrical potential? 0. Okay? So right here, if I'm going to use hydrogen as my reference half cell, this has to be 0.00 volts. Okay? All right? Every reference half cell has to have an electrical potential of 0.00. So this is from the data booklet. I haven't changed anything actually. In relation to that hydrogen half cell, where's the copper 2+? It's you said 0.34, right? And it's a positive 0.34, right? From your data booklet, correct? Okay, does everybody understand so far? Are we good? I'm getting these right from the data booklet. I haven't changed anything yet. This is actually right from the data booklet. And the zinc 2 positive is what? A negative 0.76? Okay, 0.76 volts. Yes, good? Okay. Now, I probably shouldn't have done that here because I'm not going to have any room for the, I'm going to do this actually. Do you agree so far though? Are we good? Okay? Because this is kind of the important part here. Good? Yes? Questions, anyone? That's just right from the data booklet. Look up the numbers. Okay? Okay. The next one here is the copper one, right? And then we got the zinc one here, right? Okay. So let's look at copper now. Okay? Now, I'm going to change this table. Basically, I'm going to change my data booklet, is what I'm going to do, without changing it. And I'm going to say, okay, what is the electrical potential based on what happens if I pretend that copper is the reference half cell? So I want to reference everything back to, that's why it's called the reference half cell. I want to reference everything back to copper now. I want to pretend copper is the kind of the neutral one, okay? The 0, because that's what a half cell is, reference half cell, is the 0. What if I pretend that, yeah, the copper half cell here is the 0 volts, okay? So I want to adjust my data booklet basically based on, not hydrogen anymore, based on what copper would be. What would the numbers be in relation to that? How does this table change? Well, let's take a look. My point before was this. Okay, no matter what, the difference between them has to stay the same, correct? No matter what. So this is, do you agree that copper is 0.34 volts above hydrogen, right? So if this is 0.34 volts above hydrogen, what does this have to be? Minus 0.34 volts. Okay? Understand? Questions before we move to the next one? Yes or no? Good? Yeah. The difference is always the same. Yes. We're just picking a different, all we're doing is picking a different cell to basically base all the other numbers off of. Instead of the hydrogen one at 0, I'm now going to pretend that the copper one is the 0, and everything's going to relate to that number there. Yeah.
So when you do C minus 8 gives you the net?
Yeah.
The net would be the same?
The net's the same. Yep, absolutely. Yep. Okay. All right, let's take a look at zinc here. How am I going to figure that one out? Well, let's see here. If this was 0 here, this has to be what? 0.76 below it, right? So what's 0.76 below this one has to be the same, right? If this is 0.76 below, this still has to be 0.76 below, right? So what is that? That's a negative 1.10 volts is where that would end up at. Okay? 0.76 below negative 0.34. Okay? Good? I think that's what it is, isn't it, when you add those two up? I'm pretty sure it is, yeah. Okay? All right? So what we've done now is we're not changing anything, guys, really. We're just saying, I don't want to use the hydrogen as the half cell, reference half cell. How can I adjust my table so that copper is the reference half cell? And I'd say, well, all these numbers here would depend on whether it's above or below, but the difference has to stay the same, always. Always. You can't change the fact that copper is 0.34 volts more than hydrogen. That's always the case, okay? I don't care, so if we want to change this to 0, make it our reference half cell, fine. But this has to be still 0.34 above this. And this has to be 0.76 above this, or sorry, 1.10 above that, or 0.76 difference there. That difference has to remain consistent. The net never changes, right? Like Chase said, okay? All right? Okay, let's change it. Let's say, oh, I want zinc to be my reference half cell now. How do all the numbers change according to that? Well, let's see. Zinc initially was 0.76 below this one, right? So if this is 0, this has to be 0.76 above it, correct? Still 0.76 above it. That difference does not change. And of course, that would be a positive because we're starting at 0 here. And of course, once again, okay, if this was my 0 now, that's 0.76 above, and that's another 0.34 above. So I guess up here, this would have to be 1.10 volts above that, right? There's a 1.10 volt difference between the copper and the zinc half cell, always. Okay? Yes? Okay. So that's how you can adjust these tables, okay, or basically these, what we call these reference half cells, based on which one do we want to be the reference half cell. It's not always going to be hydrogen, okay? In some cases, we want to compare it to a specific metal or whatever the case might be, but we want to do that. And this is what we're going to do in the lab tomorrow, okay, when we go there. We're going to basically we're going to get you guys to do some voltmeter stuff. We're going to get you to see that there's actually electrical conductivity taking place here. And we're going to get you to write those numbers down, and then I'm going to get you to make a table like we're going to do today here, okay? It'll be fun. It's not very long either. It's pretty easy. The longest part will be the write-up, probably, because it's going to take you a little while to sort through all that stuff you'll see today. It's fun. You'll see. Cool. Okay. All right. Good. All right. Well, let's ask you a few questions here. So I want to ask you this here. What if the electrical potential values in the table, how would they be affected if the reference half cell was switched to become the nickel half cell? So take a look at your table, guys. Okay? Right now, on your table here, hydrogen is the reference half cell at 0. What if I wanted to switch that reference half cell to nickel instead? So find the nickel half cell. Okay? What is the nickel reference half cell? What's the number that goes with it? Negative 0.26. If I want to make that the reference half cell, what do I have to do to it? I have to what? Make it 0, right? How am I going to make it 0? Add 0.26. Okay? And you do that to everything in the table, by the way. Okay? Because I'm moving the nickel from a negative 0.26 up to 0, add 0.26. Well, if I'm going to move that one up 0.26, don't I got to move the rest of them up by 0.26 to keep everything the same? Yeah. Okay? So think about that, and that's basically what we did on the last chart too. Just a little, maybe not quite as simple as that, or maybe not more as complex, or whatever you want to call it. What about the iron 3 half cell? What's the number that goes with the iron 3 half cell? It's what? Positive 0.77? Yes? Is that right? Well, once again, if I want to make that the reference half cell, and it's at 0.77, I got to drop it down to 0. How am I going to drop it down to 0? Well, I'm going to subtract 0.77 volts from everything. On the table, right? And that would bring everything in line with the iron 3 half cell. Okay? So just be aware, right, that that's how things work, right? The important thing here is that we have to remember that every reference half cell is 0. And how are we going to make everything else fall in line with that? What are we going to do to everything else? How are things going to change if that's my reference half cell? Okay? Because it's not always hydrogen that we're going to use. Okay? You might say, well, why not? Well, tomorrow we're not going to be doing hydrogen tests. We don't have any hydrogen that we can hook up some electrodes to. So we got some metals, though. So we'll pick one of those as the reference half cell and see how far we're off. Okay? So we'll do that tomorrow. Then you get to something like this here. Okay. Well, this table here looks kind of similar, I guess, to, well, a table we would have done earlier. It says create a table of reduction half reactions. When have we made tables of reduction half reactions before? No. Lesson 2. There was one with the check marks, remember, and X's. Not that. Remember the ones that said this plus this, spontaneous, this and this? Well, that's what this is. The difference being is we're not going to rate them. Well, we are, actually. That's not true. But we're not going to rate them as spontaneous and not spontaneous per se right now. Okay, although we could. That's kind of irrelevant. But listen, if you take, you know, what did we do with that table? We organized them from SOA to SRA, right? Top left, bottom right. Strongest, weakest, right? Or strongest oxidizing agent, strongest reducing agent, right? Top left, bottom right kind of thing, right? And we kind of went based on that. We're going to do exactly the same thing with this, because isn't electrical potential or cell potential, isn't that indicative of those two half cells and how strong they are? How do you figure out cell potential from yesterday's homework? C minus A, cathode minus the anode, would tell you the cell potential there, right? Okay? But listen, I think you guys probably can see this. C, yes, true, minus A should give me this number here, correct? Okay. But remember, we are doing reduction half reactions. That is this, this is a half cell, and this is a half cell. And this is a half cell, and this is a half cell in comparison to each other. So what we need to do is we need to write out, basically, we need to organize our list of reduction half reactions from SOA to SRA based on this electrical potential, okay, the cell potential here, okay? And to do that, we have to start somewhere, right? Just like you did when you started organizing these, right? You have to start with one thing and compare everything to it. The good thing about this is I'll tell you what to start with. It says right here which one you should start with. The indium half cell is the reference half cell. The indium half cell is the reference half cell, and they'll tell you that. So when I think about this, I think, okay, well, if indium is the half cell, indium, what was it, a 3 plus or a 2 plus? 3 plus, aqueous, and 3 electrons gives me indium solid here. That is my reference half cell. Okay? And I'm going to have to grab a booklet here, I guess, because I got to flip back and forth here. Good so far? Okay? Indium is my reference half cell. It tells you that at the top. You got to read it. At the top it says that's my reference half cell, so that's got to be my 0.00 volts. We're going to use that. We're going to compare everything to it. Some of these are going to go above, some of them are going to go below, just like it did before. Some will slot in between some. So we need to leave some space. That's my point. Okay? How are we going to calculate the electrical potential of the other half cells? In other words, how do I know I know this one, it's 0.00 volts. I gave that to you. That's in the part of the question. But how are we going to figure out some of these other ones? So look. Okay, well, here's my indium half cell right here, right? Well, hey, this I just told you was 0.00 volts, right? Because it's my reference half cell. I want to compare everything to that. So if that's my reference half cell, look, it happens to be my cathode half cell in this particular equation, this one right here, yes? All right? So if that's my reference half cell, or that's my cathode in this case, my question to you is, can I figure out how much this is, my anode, to get my 0.091 volts? Because cathode minus the anode has to give me that, correct? So let's do a little math here. All right? Now, up to you how you want to do this. Some of you guys will be like, I just do this, subtract that, blah, 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 add this, whatever. Good. Don't screw it up. That's all I can tell you. Because if we do, that whole chart's going to be off, right? Can you do cathode minus anode or anode minus cathode and get the same answers? No. Can you put a negative instead of a positive and get that? No, everything's going to be messed up. So I don't care how you do this. If you're not sure, then do it this way. I'd say, okay, the net is equal to the cathode minus the anode. I'm looking at the second one, yes, right there. It says here that my cathode, remember, was my 0.00 volts. I don't know what the anode is. That's what I'm trying to find, which, by the way, would be the nickel half cell, yes? Okay. But I do know as a net, it's 0.091 volts. Okay? Good? Looking at the second one here, 0, don't know, and altogether has to give me 0.091 volts. Got to solve for the anode, or the nickel half cell in this particular reaction here. Well, let's see. 0.091 volts equals a negative A. I guess A, therefore, would be what? Negative 0.091 volts. Okay? What is A in this particular reaction? It is my nickel half cell. Right? So we need to write it as a reduction, because we always write them as reduction. We've never done anything opposite of that. So don't start now. I would say somewhere here, I don't know where exactly, but nickel 2 plus and 2 electrons is going to give me nickel, and that'd be a negative 0.091 volts. Okay? I put it down there because it's less than 0. I'm building a table just like you would in your data booklet based on only these 5 or 6 ions that I have here, basically, or half cells that I have. Okay? So that's a negative 0.091 volts. That's what I calculated the anode to be. Therefore, it's got to go there, somewhere. I don't know. Maybe something slots in between. I don't know. We'll see. But now I know the nickel half cell. So when I go back to this page here, I'd say, okay, you know what? I know that this is a negative 0.091 volts. Makes sense. Look, cathode minus the anode. C minus A, right? C minus negative A, or, well, C minus A gives me a positive 0.091, right? True? So, there you go. Now you know the nickel half cell, and now I can use that one. So I say, oh, let's go back to the top one here. This is a negative 0.091 volts compared to the indium, right? But how is that going to compare with the zirconium if I use these two, cathode minus anode, has to give me the positive 0.384. So back to the formula again, right? And, you know, you can keep doing this over and over here, basically. So the net is equal to the cathode minus the anode. I know the cathode for this particular one. It's the nickel. The nickel was a negative 0.091 volts. That's the one I just found. Minus A. I don't know what the... what is it? The zirconium half cell is. That's the anode in this case. The net, though, is 0.384 volts. Yes? Okay. How am I going to solve for my anode? Well, add 0.091 volts. Add 0.091 volts. Negative A would equal... No, I forget now. What does that work out to be? 0.475? Is that right? Okay, 0.475 volts is negative A. So therefore, A has to be a negative 0.475 volts. Okay? So the anode, which in this particular reaction, okay, cell reaction, is the zirconium. And that's a negative 0.475. So when I go back up to here and I say, okay, where is that going to go in relation to these two? Well, I'd say probably down here somewhere. Zirconium, what is it, a 4 plus? And 4 electrons gives me zirconium solid, and that's a negative 0.475 volts. Okay? So I've got 3 basically half cells that I've got now, right? Okay, good. So, you know, and once again, if you want to go back up to here and say, oh, this is a negative 0.475 volts, good, perfect. Maybe I can use that somewhere else down the road. Doesn't look like it, unfortunately, but at least I know where that goes now, yeah? There's no other zirconiums down here, so that's the only one. All right, well, let's take a look. Here's nickel again. Oh, I know nickel, 0.091 volts. What does that have to be in order to get my 0.30? So you're going to do the same math again, right? I mean, if you guys look here, the only thing is, like I said, you do whatever you got to do, guys. I'm not going to tell you what to do, but, you know, there's 2 negatives here. It's pretty easy to get these signs flipped around or add when you're supposed to subtract. And when you do that, things don't work out well, okay? So I think you kind of see the pattern here. The net is C minus A here. What do we got here? Okay, so this is the negative 0.091 volts minus A, I don't know, and the net for this one is 0.300 volts. Let's see. Add 0.091, so that's what? 0.391 volts is a negative A. A would be a negative 0.391. Is that correct, somebody? Double check. Okay. So that's a negative 0.391. In this case, my A is the niobium. Okay. So I go back to here. Oops, sorry. I go back to here. Negative 0.391. That goes somewhere between these two. Niobium, what is it? 3 plus? and 3 electrons gives me niobium solid, and that's a negative 0.391 volts. Okay? Somewhere in there. Good? Yeah? Okay. And when you think about that, like I said, we're going to go back to here for a second. We're going to say, okay, this is a negative 0.391 volts, we decided. Okay, good. Now for the next one, okay, you do have to pay attention to which one of the cathode and the anode is. So now we go to this one and I say, that's a negative 0.391 volts. What's my palladium going to be? Well, that's the cathode now we need to figure out. So I'll just do this one real quick here, guys. In this case here, once again, we just want to be careful that we know which one the cathode and the anode is. So the net is the cathode minus the anode. Well, the cathode minus the anode, in this case, the niobium, which we just found, which was the negative 0.391 volts. And the net of this is 0.505. So what does the cathode work out to be? Well, it's positive 0.391 here. And then I got to get over to this side. So subtract 0.391. This works out to be 0.2. Is it? Oh, wait. 0.1 what? Sorry, I didn't hear. 114? Really? 114. Okay, I'll buy that, I guess. Sure. Good. Thank you. 0.114. Yes? True? Okay. All right. So now I know where that cathode half cell is going to go. In this case, it happens to be palladium. So I'm going to say, oh, back up to here. Well, there's 0. So I got to put it up here somewhere. 2 plus and 2 electrons gives me palladium solid 0. What do we say? 114? 114. Okay. Now I know that one. We go back to here, for example, and I can say this is 0.114 volts. And now I can do the last one as well. Once again, this is nickel 2 plus here. What was that? A negative 0.091 volts. And I could find my cathode for that one there. Okay. Doing the math on that, what is that? It's going to be, I think it works out to be about 3. What? Sorry? 0.173. That's right. Yeah. 0.1. Oops. Just a minute here. I got to find it here. There we go. 0.173, and that was the 6. Oops. That was the W6 plus. Uh, 173 volts. Okay. And that would be your list of reduction half reactions, okay, in order of strengths to the electrical potential that each one of those half cells has, okay. And once again, that's just using the formula C minus A, using, of course, that we know that this is the reference half cell. Okay. All right. Once again, there is minuses and negatives, and you got to be careful of that. And then you got to switch it over to the other side, of course. If you just want to say, oh, the cathode is always what? The net plus the anode, that's fine. If you want to say the anode is always, you know, this or that formula or whatever kind of thing, that's fine too. But you need to make sure you kind of keep it straight and that you know. Okay, whatever you decide there. But this looks like a good table to us. W6 plus, of course, would be the SOA, and the SRA would be in the bottom right. Okay. Still. Yep. Which one? Yeah, this is a D here, isn't it? No, I think what happened was you flipped them around there. This one here, I think, is it? Yeah, it's this one here. Okay. All right. So that's kind of what you need to do with that. All right. Quite a bit of work, obviously, because you got to go through that. And for some of you guys, you will be doing C minus A for each one of those. Or, you know, if you want to come up with one formula at the beginning and say, you know, the cathode is always this and the anode's always this, and if I have to solve for one of those, I just use this formula, that's fine. Okay. You just got to do a little bit of work before time just to make sure you get the right formula. But be careful when you're doing that, obviously. Okay. Now, the next thing I'll tell you is this. The homework that you're going to get today is not does not look like a chart like you guys have there. It's a little bit more involved, which of course is good. So today, you're going to get something that looks like this here. I'm just going to pick, I don't know, that for example, and it's going to say, okay, something like that there. So the important thing to remember is, and then there's going to be a number over here, whatever, okay, give me 1.45 or something like that, let's say. I don't know, I just made it up. But listen, when you go to look at that, that's a net cell reaction, right? That's your redox reaction, correct? Yes? If you mix Sb5 plus and cadmium, that's what you would expect to get from those two half cells, because there's two half cells here, right? One is being reduced, one is being oxidized. You have to know which one is being reduced and which one is being oxidized. Because if you don't know which one's being reduced and which one's being oxidized, you don't know which one the cathode and the anode is. And if you don't know the cathode and the anode, there's a good chance you're going to mess up the numbers, because you won't go C minus A. You might be doing the opposite, which would be bad. So you have to take a look here. Sb5 plus goes to Sb3 plus. Is that being reduced or oxidized? Reduced. So this is my cathode. And I would suggest even doing that today for homework. That's maybe the first thing you should do. Is CD going from a 0 to a 2 plus? That's being oxidized, yes? That's my anode, yes? So this minus this half cells should give me this, yes? Okay? And of course, they're going to tell you in that question there somewhere which one they want to use as a half cell. And it's not always C and A. The next time you do this, this could be the A here and this could be the C here. So you better pay attention and make sure you know which one is being reduced and which one's being oxidized, because that determines which one is C and which one is A, the cathode and the anode. Okay? That's pretty important, obviously. And then, of course, this number here, whatever it happens to be, right, is based on C minus A. So make sure you know those before you start. Okay? Good? And take your time. It's going to take a little bit of time, guys, and that's okay. Okay? We got time. We got good 20 minutes here. All right? Yes? All right. If you have any questions, let me know. But